Good afternoon, professors. We are from St. Paul's Coeducational College. Our work, Incentric Subdivisions of Triangles and Iterated Function Systems, has a simple motivation. Start with a triangle. Draw the 3 angle bisectors through its incenter to create 6 daughters. Repeat this operation on each daughter to create 6 granddaughters, and so on. Continuing with this Senary-Incentric subdivision rule indefinitely, a countable family of descendants is generated. A natural question is, how diverse are the shapes of the descendants? First, we need a space of triangles. A natural choice is this equilateral triangle P sitting in the first octant of R3, where any triangle with angles alpha, beta, and gamma is represented by at most 6 points. Here is a simulation of the Senary subdivision, plotting the descendants up to the 4th, the 6th, and the 11th generation. Butler and Graham showed that the Senary descendants are dense in P, meaning that their diversity is extremely high. Instead of cutting a triangle into 6, they also cut it into 3 by truncating the angle bisectors at the incenter. We call this the ternary incentric subdivision rule. They also observed, without proof, that the ternary descendants approximate arbitrarily closely any Sierpinskian triangle, meaning that their diversity is extremely low. Why say so? It is because Sierpinskian triangle here means a triangle represented by a point in the Sierpinski triangle S in P, which is only measure 0. Here is a summary of what we have reviewed. On top of these, our research has extended the investigations to new subdivision rules using the incenter that we coined as inward and outward binary incentric subdivisions. Both begin by cutting a triangle into 2 daughters with an angle bisector, but will continue differently after the second cut. In the inward binary case, the new angle bisectors cut into the previous angle bisector, while in the outward binary case, the new angle bisectors come out of the vertex produced by the previous cut. Here are the third cuts, and the fourth cuts, and so on. And we can ask the same question: how diverse are the shapes of the descendants? In what follows, we will first prove convergence results in the outward binary case, as it is relatively straightforward. Next, we will use the tool of invariant sets of iterated function systems to prove densest results in the inward binary case, as well as to reprove those in the Senary and ternary cases more efficiently. Finally, we will use the more advanced tool of invariant measures of iterated function systems to prove the unique phenomenon of uniform distribution of the inward binary descendants. A remark before proceeding. Convergence and denseness in P are equivalent to those in its projection T on the alpha-beta plane. We have used them interchangeably, depending on which one facilitates our work. In the outward binary case, the cuts evolve like a binary tree, and we have found that all descendant sequences generated along all branches converge, but to very few possible triangles. The zigzag case's limit is uniquely determined by the starting triangle. The eventually zigzag case's limit triangle is uniquely determined by the starting triangle and where the zigzag begins. The remaining cases are more surprising. They all converge to the isosceles right-angled triangle. Hence, the diversity of the outward binary descendants is extremely low. Working in T, which I will redraw now, working in T, which is this space of triangles sitting in the first quadrant of R2, the division maps that produce the 2 outward binary daughters of a mother Q are given by D1 and D2, which are affine maps on R2. Our convergence proofs will follow from showing that certain other affine maps associated with them are contraction maps through computing matrix norms. The matrices governing the zigzag case are this matrix with one norm, 1/2, and this other matrix also with one norm, 1/2. Then the convergences of these pure iterations follow from the Banach fixed point theorem. The eventually zigzag case corresponds to eventually pure iterations, so it is a simple corollary. The last case, where both D1 and D2 appear infinitely many times in the so-called mixed iterations, is the following technical lemma on convergence in a metric space. It uses a pair of joint contraction maps with a common fixed point to generate convergence via mixed iterations. Its proof is straightforward. Finally, the last case follows from verifying that D1 and D2 satisfy the previous lemma. This is a recap of convergence results in the outward binary case. Next is the inward binary case. We have found the best tool for it, the theory of iterated function systems developed by Hutchinson, which begins with just a finite set S of contraction maps S1, S2, etc. on a complete metric space X, but ends up with far-reaching consequences. He showed that each system has a unique invariant set, which is a compact subset K of X that has its retracting property, K equals to S of K. By using the retracting property, we have proved that sorting from any point in K, its descendants upon indefinite iterations of all the contraction maps form a dense subset of K. With this powerful tool, all these densest results will be proved by the same two acts. One, show that their division maps, again affine or linear maps, form iterated function systems through computing matrix norms. And two, verify their respective invariant sets. Here we go. Firstly, the inward binary case. Here are its division maps C1 and C2 on T-bar. Mi here, with 2 norm 1 over root 2, denotes the matrices providing their contractivity. It is also easy to verify that T-bar is their invariant set. Second, the Senri case is reproved. Here are its division maps A1 to A6 on P-bar, which I will quickly redraw. And Ki prime here, with 2 norm root 3 over 2, denotes the matrices providing their contractivity. P-bar is their invariant set, also easy. Finally, the ternary case is proved in the same manner, where Butler and Graham only observed but didn't prove. This finishes our denseness proofs. But there's more. As we simulated inward binary subdivisions, the descendants look more and more evenly spread over the space of triangles. So would it eventually become the uniform distribution? The answer is yes. More precisely, we have proved that the sequence of empirical measures of the descendants converges weakly to the uniform probability measure on P-bar. In fact, our discovery marks the first known limiting distribution. Butler and Graham mentioned that the Senri case should have a limiting distribution, but were unable to determine it. To prove the weak convergence, we had to go deeper into Hutchinson's theory. He constructed this contraction map phi, which, by the Banach fixed point theorem, has a unique fixed point kappa. This so-called invariant measure of the iterated function system is also the weak limit of iterates of phi. To finish our proof for the weak convergence, we only had to verify that the uniform probability measure on T-bar is the invariant measure of the iterated function system consisting of C1 and C2. Here is a summary of what we have proved. Using the same techniques, we also managed to generalize this convergence and this denseness result to outward and innery quasi-incentric subdivisions respectively. Both release bisecting angles to dividing them in a fixed ratio. Here is the inward binary quasi-incentric subdivision and the outward binary quasi-incentric subdivision. The unique uniform distribution phenomenon in the inward binary descendants is unique as it doesn't happen in the other quasi-cases. This concludes our presentation. Thank you.